For the three of you who prefer geometry over algebra, here is another proof of the product rule. This one, of course, a geometric proof. Or maybe you were having a hard time with this whole fancy zero. How would I even know to add or subtract that fancy zero? Well, you don't have to worry about that with this particular proof. So let's let u and v be functions of x, and then we're going to let p of x be equal to the product of those two functions. And we're going to represent it geometrically with a rectangle, right? So we have the product of u times v. Geometrically, the area of that thing would, of course, be u times v. All right, and now we're going to change the area. We're going to change the area by increasing the v by some width and the u by some width. And I'll call that delta u. All right, so let's see how the area changed for this part. It should just be the v times delta u. All right, and then I'm going to do the same thing over here. I'm going to change the v, the width down here, this base length by some small increment, which I will call delta v. And how much do we just change the area by? It would be u times delta v. And then finally, our shape here is now u plus delta v and u plus delta u. So I need to fill in this little gap right there. And then we just change the area by delta v, delta u. Okay, so we're going to write the change in area, or the change in P here, is equal to just these three rectangles added together, right? That's how much we changed this area by. So V delta U, U delta V, and finally delta U delta V. All right, doesn't look much like slope to me. In order to have slope, don't we have to have delta y over delta x? We sure do. So let's fix that by just dividing everything by delta x, right? We can divide both sides of an equation by a particular number. We're going to divide it by delta x. And now we have slopes. But specifically, we only have slopes of secant lines, right? This is like the change in y over change in x. So what do I have to do to that in order to get slopes of tangent lines, which is what we associate derivatives with? We got to take the limit as the delta x down here, which is like our h. Delta x goes to 0. So that's what I'm going to do next. I'm going to take the limit as delta x goes to 0. Now, let's talk about this item by item. So over here on the left-hand side, I have delta p over delta x, taking the limit as delta x goes to 0. Again, this is like change in y over change in x. If you take the limit of this as that delta x goes closer and closer to 0, the slope of the secant line is approaching the slope of the tangent line, which we will write as dp dt, right? That's that Leibniz notation. And the usefulness of that Leibniz notation is the fact that there's this easy visual relationship between that secant line and that tangent line. All right, so now let's take it term by term over here on the right-hand side. I have v delta u over delta x. Well, ignore the v because it's not affected by this delta x, and we have a delta u over delta x. That's a slope of a secant line, and with this limit, it's going to go to the tangent line du dx. So we have v du dx. Likewise, on the second term here, you have u. It's not affected by this delta x, but the delta v over delta x, that secant slope will go to the tangent slope dv dx. All right, so far it's starting to shape up, but I got a little bit of a problem right here. Like, who do I give this delta x to? There's two of these up here. So what I'm going to do is I'll split it up. I'll give it first to the u, and then to get one on the delta v, I need to multiply this by a fancy 1, and my fancy 1 is just going to be delta x over delta x. Right, it's just a 1, and now I'm going to take this delta x, I'm going to pair it up with this delta v, and then I'm going to have an extra little delta x hanging out. Okay, how did that help me? Well, on this first term here, this delta u over delta x, that secant slope will go to a du dx, just like that one. This will go to a dv dx, and then what will the delta x go to? It should go to 0. So this is what you get. And you take the 0 multiplied times these two tangent slopes, that's going to be 0. And we have the product rule. Okay, but let me rewrite it in a form like we saw in, say, the previous proof, like this. We have P prime is equal to U times, or V times U prime plus U times V prime, but I don't like it like that. You know how I like it. It's like this. It's the derivative of the first times the second plus the first times the derivative of the second, like I said. And when we see this in just a minute, if we think of it in those terms, it'll be easy to extend out to as many products as we want. So here then formally is the product rule. The product of two differentiable functions, f and g, is also differentiable such that we got the derivative with respect to x of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x, or informally we'll just say the derivative of the first times the second plus the first times the derivative of the second. Remember, it's these twins dating twins. And over here on the right-hand side, I was able to scour the internet and got you a picture of Leibniz circa 1675. Okay, so like I said, we can take this product rule. It doesn't have to be just two functions. What about three? Here's what it's going to look like if we have three differentiable functions, f times g times h. Now, this might be kind of tough to see, so let me maybe zoom in a little bit. Come on. There we go. Just a little. So notice where the derivatives are for each one of these. So it's like the derivative of the first times the second two. And then it's the first and the last one times the derivative of the second one. You just put the derivative right in the middle. Plus the first and the second one times the derivative of the last one. And again, you can extend that to as many of these products as you want to. Just keep that same exact pattern.